everyone, I hope you're doing well. This is a video tutorial for Workshop 9. I strongly encourage you to also do Workshop 9 on your own, typing in the code manually and running it so that you can do it on your own computer. This is just going to walk you through it to make sure that you get a chance to hear a little bit more about it, okay? And to hear it from a live person, So, Workshop 9 is about multivariate regression. We learned this last Monday and last Wednesday, and you used it in your lab on Thursday. Great job, by the way. So we want to know how good is our model. And we can use two model statistics to do this. You've already learned them. One of them is called R squared, and one of them is called the F statistic. R squared is the percentage of variation in the outcome explained by our model. It ranges from 0 to 1 or 0 to 100%, right? It's a very intuitive statistic. There's also the F statistic, which ranges from 0 to infinity. It measures how much better is our model than the intercept. And remember, the intercept is a single value of y, independent of everything else. It's like how much of the outcome would you expect to get if none of the other things mattered? And so we had better hope that our model is better than the intercept. Otherwise, I mean, that's a bad model, right? Okay, so we're going to use the diamonds data set to understand this a little bit better. We're going to load the tidyverse package, which I have up right here. We're going to run this function on diamonds, and this is not super necessary, but it means that we're grabbing only 1,000 randomly sampled diamonds instead of 50,000, which would be a lot for our computer. And we're just going to grab the price and the carat of those diamonds. Now, if we run dat, you'll see down here that we've now got the price and carat of those diamonds. So this is like $807, and this is 0.4 carats for a single diamond, all right? We're going to do one other quick trick, which is we're going to rescale the variables. This is just going to help later with the visualizations. Later, we'll talk about rescaling. This is how you do it. So we are just going to create a z-score for each variable, which means that things go from units of dollars into units of standard deviations. Okay, boom. Don't worry about it too much. We can see what it looks like now. Okay, so this was before 807. This is now negative 0.77. It just means that this is a really, really low value. It's really far from the mean, that sort of thing. Okay. Great. So we've rescaled our variables so that they're going to be helpful to us. We can now run this model right here, much like you've done before. And you'll see that it created n. Let's check out n. Okay, so it looks like when we run m, we get the model equation, which suggests that, let's see, our intercept value tells us how much, what price would we expect to get if nothing else really mattered. And that is a very, 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 very small price. So this suggests that most diamonds usually are like pretty worthless, right? And then our carat over here is our beta coefficient for carat, right? So intercept is alpha, and this is our beta coefficient. And this says how much, how expensive, what price do we expect, what change in price do we expect when carat goes up by 1? Okay, so carat went up by 1. We expect the price of our diamond to be $0.9 more. So 90 cents more. Great, that's kind of useful. We can get some other stuff out of our model too. If we put this up here, we'll see there's a ton of stuff contained in this. There's coefficients, there's residuals, fitted values, this thing called model down here. Let's walk through a few of them. Most of them don't matter, and but one of them is fitted values, which I have right here. These are the predicted values for the outcome variable that our model generated. So it's kind of cool. Like we can these are the values of the best fit line. Neat, right? We can also get something called M residuals right here. If we run these, it's just going to be a lot of numbers again, but these are actually the numbers. This is how far our prediction is from our observed, or our observed is from our predicted. Okay? Because residuals equal the observed minus the predicted value of y. Okay? Great. So we've got these measures, and these can be very useful to us, especially when we're trying to assess how good our model is. There's one other thing that we've got called M model. If we check this out, these are a lot of numbers, but in particular, they are our original values for price and carat scaled, right? So that's cool. So inside our model, we have under this thing called model, so M $model is the data that we inputted. We've also got the fitted values, the predicted values that our model generated, and we've got residuals, which is how far off we were. Pretty useful. We can actually create a single data frame with all of these in them so that it's easier to view. And we would do it like this. I'm going to create a data frame called MDAT, where one vector is going to be predicted values, and I can specify that I want to be fitted. I want it to be this particular vector. We can get our residuals and name them residuals, and we can pull them from here. And then we can also grab all of the variables that were in M model and stick it in there. So if we run this and run it ourselves, boom, lots of numbers. Let's check this out. What's happening at the top? Okay, great. So we have the predicted, the residuals, the price, and the carat, exactly in the order that we wrote them. And one quick trick, I like to use head. It shows me things, just the first 6 rows, so I don't have to scroll. Great. So we've got a bunch of important kinds of information about our model all in a data frame called MDAT now. We could very easily visualize this. Okay, so over here, can you see this? This is the first visualization. This is the best fit line between carat and price. Now you may have noticed, hey Tim, I thought that this was going to be a multivariate model. This is actually just this just has 2 variables in it, not 3 or more. It works the same for all of them. So we can see, okay, this blue line, these are our predicted values. These prices, these dots are the price by carat, okay? And the ones that are further away from best fit line have bigger residuals. Okay, so that's useful. Wouldn't, just as a sort of second check, let's observe those residuals a little better. Same line, same data. Now this is just showing us that the spots, the points that are further from the best fit line have bigger dots. And this distance between them, these are the residuals. If you have more residuals, it's a bad model, because the trend line isn't really close to them. It doesn't predict them well. If you have small residuals, that means it's a better model. So we're looking for overall, on average, are our residuals good or bad? Okay, so what comes next? By the way, the code in this workshop uses some extra code. You don't need to know it. I'm just using it so that you can visually see this regression model, okay? So we can actually do a pretty cool thing here. R squared is pretty easy to calculate. I put the code right here, and it's in your workshop code too. Using our data frame of model inputs and the model outputs like predicted and residual, we can create two summary statistics. These are the total sum of squares and the sum of squared residuals. Okay, what does this mean? First, we're going to calculate the total sum of squares. And we can see right here that what we're doing is we're taking the price and we're subtracting it by the average price. Then we are going to square that value so that positives and negatives don't matter anymore. And we're going to add all of those together. Okay, so let's look over here in this visual. The average price would be a line sort of going through here, right? And if your price tends to be further from the average price, that means your data varies, right? It's not all at one value, it varies. If your price is further from the average price, top or bottom. So the total sum of squares is the total squared variation in the data. And the sum of squares is actually it's like how bad our model is. Okay, so we can calculate the sum of squared residuals by taking the price, the observed price, like this one, and subtracting from it the predicted price, like this one, right? So observed, predicted. And that's going to show us how far off is our prediction. You may be thinking, sounds familiar. It should. This is a residual, right? So we take the residual, we square it so that positives and negatives don't matter, and then we add up all of those squared residuals. The sum of squared residuals is literally the sum of squared residuals. It's kind of cool, right? So what this means is we have two measures now, the total sum of squares and the sum of squared residuals. Put in different terms, we have how much variation does occur in our data and how much variation isn't explained by our model. Okay, total sum of squares, all the variation. Residual sum of squares, unexplained variation. We could think of this as a fraction, where if you took the sum of squares, sum of squared residuals, you divided by the total sum of squares, you would get the fraction of how much of the variation isn't explained by our model. And that's kind of helpful, right? What would be even more helpful is if we could find out what percentage of variation is explained by our data, right? So we could take 1 minus the sum of squared residuals divided by the total sum of squares, which is exactly what we do here. And if we run this, it's going to output right down here a really, really, really handy set of measures. We've got the total sum of squares here, which equals 999, which I guess is like in dollars, I guess. We've got the sum of squared residuals here, which is how far off are we. And we've got r squared, which is 1 minus this divided by that. 1 minus the sum of squared residuals divided by the total sum of squares. The value of r squared is 0.85. This means that 85% of the variation in price was explained by our model, which actually is like really astonishingly high for R squared, right? That is a really good model to be explaining 85% of the variation. And you know, the cool thing is, R squared is a really, really commonly used but kind of complex statistic. And we calculated it by hand right here. So, some news. You will never have to calculate R squared by hand. But this is how you do it. And I hope that you understand a little bit better what it means. It's the percentage of variation in the outcome explained by the model. Okay, so we've done that. But here's the thing. I promised earlier that you could visualize all statistics, right? That all statistics are single numbers that summarize something going on in data. And we can kind of see that. Here's kind of what it would look like, okay? Let's take a look at this. So we've got blue and we've got red. The blue is the total sum of squares, and the red is the sum of squared residuals. How did we make this? For every point, we drew out the residual between the observed point and the predicted point. Okay, so it's right there. And then we squared it, literally making a square. See that right there? This is, if you take this box, this area, and you add up all of them, this is literally the sum of squared residuals. Okay, neat. So we can say that our data tends to vary out this much, okay? Sorry, let me say that again. We can say that our data tends to be off this much for this data point, and we can find that for all data points. We can add them up, and we get the sum of squared residuals. However, we can also draw the average price. This dotted line going through here. This is the average price. And what we can do, I'm actually just going to check that real quick. Yeah. The minimum is the average price, okay? And we are able to draw squares that begin at the average price and go up to the observed price, right? So like, I guess somewhere out here there must be an observed price, okay? Here. When we draw a square from this point down to the dotted line, and this is going to be how far away each diamond's price is from what we predict on average, right here. We can square it, and so that shows us kind of how much that data point varies compared to the mean. We can do that for all of the observed data points, creating a whole bunch of squares, and it's going to be the total sum of squares. We can kind of say that like this blue represents the total possible variation in the data, but the red is the unexplained variation in the data. R squared tells us how much, what percentage was explained. Okay, so it's kind of like, you could think of it as this blue part, but not the red. The blue part not covered up by the red. Okay, nifty, right? I won't worry about it too much. The main thing to remember is that R squared is the percentage of variation in the outcome variable explained by our model. Okay? Cool. So lots of code. Wow, ggplot is amazing. Yay. Okay, great. Moving on. There's another thing that we might want. Great. All right. We might want to calculate something that we can get statistical significance with. We can do this using the F statistic. Just like in ANOVA, we made an F statistic from 0 to infinity that measured the strength of the association between variables. We can also make one for this. Here's how it works. We're going to calculate the residual sum of squares, or the sum of squared residuals. I shouldn't have changed the name for that. They're the same thing, right? Okay. Price minus predicted squared, sum of all of it. It's still residuals, right? Okay, so we get the residual sum of squares, and we get the total sum of squares just like we did up above. Okay? We can also get the sample size, so the number of diamonds, and we can get the number of different variables in our model, which in this case, I am grabbing using this code. I'm saying, hey, find the column names of our model, and now tell me how many names there are. So price and carat. So P equals 2. Great. And then we really want to know what the explained sum of squares is. And that is the total sum of squares minus the residual sum of squares. It's how much variation was explained. Okay? So if we run this, we can get a data frame of ingredients for the F statistic. Let's check it out. All right. So we can see that the explained sum of squares is the amount explained. The total sum of squares is the total variation in the data, and the residual is how much wasn't explained. We can see that this plus this equals that. Excuse me. We can also see our sample size is 1,000, and we have 2 variables. Great. The F statistic can be computed here. What this does is it creates a few more measures that are important to know in the back of your head, but again, they don't really affect your day-to-day use of the model. So first, we calculate the mean squares due to regression, given the number of predictors. So it's how much variation was explained, given how many predictors you used. Okay, so, and we take P and we subtract 1, kind of to be conservative. Actually, no, not to be conservative. It's because one of P is always the outcome variable, right? Because we had price and carat. Carat was our predictor, price was our outcome. So 2 minus the outcome leaves just P minus 1, okay? Then we're going to get the mean squared error. That's how much variation in price was not explained. Kind of controlling for the sample size and number of variables. So for that, we take N minus P. And we calculate the mean squared error as the residual sum of squares divided by the sample size minus the predictors. Okay, great. So this has given us our 2 final ingredients. And if we take the mean squares due to regression, so like how much was explained given the number of predictors, and we divide it by how much was not explained given the sample size and number of predictors, we can get the F statistic. And we can use a hypothetical null distribution to get the p-value. This last part, not super important. You guys have learned how to do it via permutations. It works pretty much the same way. It just relies on a large sample size. Okay. So let's check this out. Boom. So if we look at this now, we can see the ingredients that we made. We can see what the explained sum of squares was, and the mean squares due to regression, which is actually the same because it's 2 minus 1. P was 2 minus 1, right? We can get the mean squared error, and we get this F statistic. This F statistic is crazy high, right? It ranges from 0 to infinity. That is not close to 0, right? So that means that our model explains the variation much better than the intercept would. And because that value is so extreme compared to all of the possible F statistics we could have gotten, we say that its p-value is 0. The chance that we're wrong is pretty much 0. We're like 0.00001, right? Okay. Okay, so you've learned the math, the real math behind these measures. I highly doubt that you will ever need to explain to someone how this works. But you do need to know how to interpret these. You need to be able to casually use these terms when you write about stats, when you think about stats, when you do analysis on data. So you have this as a resource so that you could pull it up and explain to someone how these numbers are made. And for your working knowledge, you should know what we learned at the very beginning. R squared is the percentage of variation in the outcome that's explained by our model. The F statistic is a number from 0 to infinity that measures how much better our model is than the intercept. Than a simple, straight, horizontal line. And you can get a p-value for the F statistic. That's going to tell you how statistically significant our model is. It is possible to have a high R squared and a low F statistic, an insignificant F statistic, but it's not likely. They generally trend together, okay? You could have a low R squared and a high F statistic, and that means that even though we haven't explained all the variation in the data, even though our R squared is low, our model still significantly explains the variation better than a straight line would. Okay, so it's still a useful model. Okay, so we learned today all this stuff. What if I told you there's a single simple code you could use? Check this out. This shows us our residuals, our coefficients, our estimates, the significance of our estimates, our R squared, our F statistic, and our p-value. So that's all you need. We'll talk more soon. I'm going to upload more of these videos. I hope this has been helpful, and please be sure to be in touch if you have any questions. All right, good one.